This project is for CSCE 522 with Dr. Farkas. My name is Nate Fuller, and my partners are Daniel Bauer, Bill Brower, and Sabrina Wilkes Morris. Our credentials are as follows. For myself, I have taken a summer cyber education course at the Air Force Institute of Technology in Ohio, where we learned about computer and digital forensics and how to investigate computer crime and gather evidence. Daniel Bauer has had algorithmic design courses that have benefited him in his understanding of intrusion detection algorithms. Sabrina Wilkes Morris is an intrusion detection analyst responsible for managing intrusion detection devices, and Bill Brower has taken algorithmic design and discrete mathematics courses. Our project is on computer forensics with a specific focus of intrusion detection. In this video, I will talk more about intrusion detection systems, specifically their problems and recent solutions to help minimize the problem. It is relatively common to use both signature-based and anomaly detection-based intrusion detection systems in unison. However, labeled data to train and update the signature-based IDS is costly, and purely normal local network data to train the anomaly-based IDS is difficult to collect and curate. We surveyed current IDS research to come up with a potential solution and found that semi-supervised approaches have potential. More specifically, semi-supervised anomaly detection algorithms grounded in unsupervised learning can be trained on partially labeled datasets that include intrusions. Labeling must be done by hand, and it requires a significant amount of domain knowledge on the part of the labeler. But unsupervised machine learning algorithms can be used to separate intrusions from normal network data and identify specific instances that should be labeled by hand to create an effective partially labeled training set out of unfiltered local network data. It does not take much labeled data, 10 to 15%, for semi-supervised anomaly detection algorithms to be significantly more effective than traditional anomaly detection methodologies, and once the data is labeled, it can also be used to train signature-based IDS. Finally, the issue of keeping signature-based IDS up to date can be resolved by generating signatures for new threats as they are caught by the anomaly-based IDS. This project is for CSCE 522 with Dr. Farkas. My name is Nate Fuller, and my partners are Daniel Bauer, Bill Brower, and Sabrina Wilkes Morris. Our credentials are as follows. For myself, I have taken a summer cyber education course at the Air Force Institute of Technology in Ohio, where we learned about computer and digital forensics and how to investigate computer crime and gather evidence. Daniel Bauer has had algorithmic design courses that have benefited him in his understanding of intrusion detection algorithms. Sabrina Wilkes Morris is an intrusion detection analyst responsible for managing intrusion detection devices, and Bill Brower has taken algorithmic design and discrete mathematics courses. Our project is on computer forensics with a specific focus of intrusion detection. In this video, I will talk more about intrusion detection systems, specifically their problems and recent solutions to help minimize the problem. Most organizations do not have the kind of manpower that would be necessary to gather that kind of data manually, once not to mention on a continual basis. To overcome that, machine learning algorithms are almost always used to both build models and keep them updated. Machine learning algorithms can be broken down into two types, supervised and unsupervised. Supervised algorithms work by learning how to classify input based on label training data, and unsupervised algorithms work by learning how to classify input based on statistical clustering in raw unlabeled data. Technically, both can be used to generate models for anomaly detection, but labeled training data is cost prohibitive, and it, in practice, shares a lot of pitfalls that scenario misuse-based algorithms have, because only known attacks are present in the training data. That said, unsupervised machine learning algorithms are more commonly used. Unsupervised learning also comes with a catch, though, in that in order to be effective, it requires a large amount of strictly normal traffic as training data. If the training data contains intrusions, the algorithm will have trouble detecting those types of attacks in the future because it will assume that they are normal. Unfortunately, purely normal training data isn't any more readily available than labeled training data. Moreover, network data from the system being monitored is ideal for training, but it is hard to guarantee that no intrusions took place while the data was being collected. To that end, our goal in this paper and presentation is to outline a solution that lessens the need for clean training data so that anomaly-based IDS systems can be more effective as a turnkey solution. Our proposed solution is multi-pronged. Number one, we want to reduce the need for purely normal training data and unsupervised machine learning algorithms that are used to separate intrusions from normal network data and create a labeled training set out of unfiltered local network data. This can be improved upon by using a semi-supervised approach that utilizes a small amount of pre-labeled data to help label the raw data more accurately. Number two, the labeled training data that was generated in Step 1 can be used to train both types of IDS systems. Co-utilization of signature and misuse-based IDS allows faster responses to known attacks because it avoids the minimum length observation window inherent to anomaly-based IDS. Meanwhile, anomaly-based IDS systems act as a second line of defense against threats that haven't been seen before. Third and finally, the anomaly-based IDS systems can be leveraged to keep the model for the signature misuse-based IDS up to date by generating signatures for previously unknown attacks. We will now talk about the future improvements. For unsupervised anomaly detection, the sensitivity of the unsupervised anomaly detection obviously needs to be improved. At 40 to 50%, the detection rate is not much better than just randomly guessing, but its low false positive rate is encouraging, as is its performance when compared against supervised methodologies. One possible way to improve upon unsupervised anomaly detection is to experiment with how data is clustered and labeled. One of our sources, Portney, was motivated primarily by speed so that they could use a variation of single linkage clustering and labeled clusters as normal or anomalous based for the relative number of instances they contained. There are plenty of more performant clustering algorithms that could be used instead. There is also a lot of room for improvement in regards to unsupervised anomaly detection being a turnkey IDS solution. At the moment, performance is still largely tied to the quality of the training data and how well it meets the requirement of representing a wide variety of intrusion and normal subtypes. And while that is not likely to change because machine learning is only as smart as the training it is given, a non-algorithmic solution such as open sourcing high-quality data sets for supplemental training could be a viable way to make progress in that regard. Finally, the detection of denial of service attacks could be improved tremendously. At the moment, the algorithm does not do a good job of detecting denial of service intrusions because making one happen involves such a large amount of network traffic that it makes the assumption about the rarity of intrusions relative to normal traffic invalid. Regarding semi-supervised anomaly detection, a new way to improve semi-supervised anomaly detection is through acquiring labeled examples. Many topical real-world applications involve millions of training instances so that domain experts can only label a small fraction of the unlabeled data. Active learning deals with finding the instances that once labeled and included in the training set lead to the largest improvement of a retrained model. Most of the time, an active learning step is followed by an optimization step of the semi-supervised anomaly detection and in order to update the model with recently labeled data. This procedure, of course, takes up much time and can be altered for practical settings. One example is by querying a couple of points before performing a model update. Irregardless of the actual implementation, alternating between active learning and updating the model should be repeated until a desired predictive performance is obtained. This concludes our project on intrusion detection systems. Thank you for watching, and please let us know if you have any questions.